Welcome to this explainer. If you're a focused learner who loves getting straight to the core of how things actually work, well, you are in exactly the right place. Today, we're taking a deep dive into the fundamental physical parameters of soil. We're going to build our understanding of the solid, unchangeable particles all the way up to the dynamic forces of compaction. Let's get right into it. To do that, we're using a bottom-up mechanics approach. We'll start with the two types of soil density, then observe bulk density in action. After that, we'll explore porosity and soil pores, and finally, wrap up by examining the dynamics of soil compaction.
All right, Section 1, two types of soil density. Now, whenever we talk about density, it's absolutely crucial to know how we're actually measuring it. In soil science, density is the weight per unit volume of a substance, commonly expressed in megagrams per cubic meter, or mg, m to the minus 3.
So there's a pretty stark contrast between our two main measurements here. First, we have particle density, which is simply the mass per unit volume of the soil solids themselves. This is a permanent character. It's completely unaffected by things like tillage or depth. But then we have bulk density. This is the mass per unit volume of dry soil, meaning it includes both the solid spaces and the pore spaces. And because it includes those empty voids, it's highly variable and heavily influenced by compactness.
To put this into perspective, specific mineral composition strictly determines particle density. For most mineral soils, this number actually varies within very narrow limits. But check out the extremes on this table. Humus sits way down low, between 1.3 and 1.5. On the flip side, heavy minerals like pyrite and hematite reach all the way up to 4.9 and 5.3. Basically, the physical makeup of the solid entirely dictates this baseline. Moving right along to Section 2, bulk density in action. While particle density gives us that permanent baseline, bulk density is honestly of far more importance when we want to understand the actual physical behavior of soils out in the field. And to measure it, well, the core sampler method is the one most widely used. The really crucial point here is understanding what a normal bulk density even looks like. In normal soils, it generally ranges from 1.0 to 1.60 megagrams per cubic meter. But let's look at how that baseline shifts. If you're looking at an organic peat soil, that number drops all the way down to just 0.5. But if you're dealing with compacted subsoils, it shoots right up to 2.0.
So what exactly pushes that number up or down? Well, it's a direct relationship. More pore space simply means less bulk density, while higher compactness means more bulk density. Specific field conditions play a huge part too. Higher depth of soil, that means more bulk density. Finer textures actually result in lesser bulk density, and high organic matter content leads to reduced bulk density as well. Structure totally matters too. A crumb soil structure shows lower bulk density than a platy structure. And of course, human action plays a huge role. Tillage temporarily reduces it, but cropping actually increases bulk density in topsoils.
Which brings us perfectly to Section 3, porosity and soil pores. If bulk density is heavily influenced by empty space, we really need to understand that space. Porosity simply refers to the percentage of soil volume occupied by pore space. These voids constitute the portion of the soil volume not occupied by solids, and their main job is holding air and water.
But not all empty space is created equal. We classify soil pores into two main types, separated by a threshold of 0.06 millimeters. Macropores are the large ones, greater than 0.06 millimeters, that allow air and water to move really readily. Micro or capillary pores are smaller than 0.06 millimeters, and in these tiny spaces, the movement of air and water is restricted to some extent. Ideally, what you really want is an approximately equal number of both macro and micropores. That balance facilitates the absolute best drainage and aeration. We can actually break these pore sizes down even further into specific size ranges measured in microns. As you can see, coarse pores are greater than 20 microns, medium pores range from 20 to 200, fine pores are between 2 and 20, and very fine pores are incredibly tiny, less than 2 microns. Generally speaking, clays and clayey soils possess a much greater number of those vital micro-capillary pores. Okay, let's look at exactly how we calculate this using the metrics we've just covered, walking through a problem right from the source material. Step 1, we take a soil core and measure it. We find a cylinder volume of 73.5 cc, a dry soil weight of 87.8 grams, and we know our particle density is 2.65 grams per cc. Step 2, we calculate the bulk density. We just divide the weight of the soil, 87.8, by the volume, 73.6, which gives us a bulk density of 1.19 grams per cc. Finally, step 3, we calculate the percentage of pore space. We take 100 multiplied by 1 minus our bulk density divided by our particle density. So 100 times 1 minus 1.19 over 2.65. This gives us exactly 55.10% pore space. Just think about that. Over half of this particular soil volume is entirely empty space.
Just like bulk density, porosity is totally prone to change. Let's look at the factors at play here. Soil structure is a big one. Granular or crumb structure simply has more porosity than single-grain soils. Texture matters too. Sandy soil has a small total space, whereas clay has a higher total space and more micropores. Organic matter is fantastic because it facilitates more aggregation and porosity. On the flip side, depth decreases porosity due to subsoil compactness. We also have to consider living organisms. Earthworms, rodents, and insects actively increase macropores. And finally, cultivation. Intensive cultivation lowers porosity because it reduces organic matter.
And that idea of reduced porosity leads us perfectly into our fourth and final section, the dynamics of soil compaction. Compaction represents the dynamic behavior of soil, encompassing compression and a real increase in density. It is, quite literally, the physical squeeze.
Now, water actually initially decreases friction to help facilitate this compaction, but it ultimately hits a strict physical limit. This limit is called the Proctor moisture content. It's the critical limit during compaction where adding any more water just does not increase density anymore. Why? Because of the inherently incompressible nature of both soil solids and water itself. When this heavy mechanical squeezing happens out in the field, tilling practices can create a specific restricted layer, causing surface and subsurface compaction. In a lot of soils, this leads directly to a feature termed the plow sole. This is a distinct, highly compacted layer commonly found right at the bottom of the zone of plowing, very often caused by heavy farm equipment or wooden plows.
We generally view compaction as a major problem because it restricts root penetration and nutrient uptake. But, interestingly enough, in highly coarse-textured sandy soils, compaction actually enhances water retention. It does this by increasing the micropore space. So, by forcing those particles closer together, it actually helps reduce percolation loss. Which leaves us with a really fascinating tension between compaction's negative mechanical resistance and its positive water retention effects. So, I'm going to leave you with this provocative question to ponder. Since compaction increases micropore space in coarse soils, how does the dynamic behavior of soil change our entire understanding of perfect porosity? Thanks so much for joining me on this explainer.